Hello and namaste everyone. Welcome to lecture 37 of this NPTEL course on stochastic approximation. So if you remember in the last week and this week we have been looking at some motivation for two-time scale stochastic approximation and stochastic recursive inclusion. Towards that we looked at solving a linear system of equations where we have access to only the samples of this right hand side vector. So Ax equals expected value of y and we have access only to samples of this y. On top of that we are presuming that some of these measurements come from faulty sensors or adversaries, right, and to deal with that we came up with an algorithm and we said that that algorithm necessitates use of two-time scale stochastic approximation because the gradient of this L1 objective that we considered, right, results in a sign function which does not allow the expectation and sign to interchange freely, right, and that necessitated two-time scale algorithm. And because of the presence of adversaries and also because of the subgradient nature of the algorithm, right, subgradient descent nature of the algorithm, right, we were forced to consider set valued interpretation of the update rule, right. And in the previous class we said that first let us try to see, at least in an idealized setting, what is the behavior of the algorithm. In particular we looked at the limiting differential inclusion, right, and we showed that at least all solution trajectories of the limiting differential inclusion indeed converge to the the desired solution, which is expected value of x, right. So that is in the idealized setting. What remains to analyze is the behavior of the original stochastic algorithm itself, which, as I said, has this stochastic recursive inclusion interpretation, and in the next few classes we will give a formal convergence analysis for this stochastic recursive inclusion. So let us discuss things in detail, right. So as I said, this was the limiting differential inclusion that we looked at, and we showed that every solution trajectory of this limiting differential inclusion converges to expected value of x. So our goal right now is to extend this discussion to the level of the convergence of your stochastic recursive inclusion algorithm itself, and recall that xn had the update rule that is given over here, that is, it is xn plus alpha n sine of yn of in plus 1 minus ain plus 1 transpose xn times ain plus 1, right. Here your in plus 1 was sampled uniformly from the set of indices 1 to n, right, and this little yn, at least for honest coordinates, right, tries to approximate your expected value of y of I, right. So it basically takes the running average of the observations for this coordinate y of I. So you can look at the update rule that we had discussed in the previous class, right, and then I said that okay, this update rule can be rewritten in this form, right. So we can rewrite this as h of xn yn plus epsilon n plus mn plus 1 1, right, where h of xy is having this expression with expected value of y, that is this idealized expression at least for I in the set of non adversaries, and this is the expression that we cannot in some sense control because here I belongs to the set of adversaries. So we said okay, let us define h of xy in this fashion. However, the update rule does not have h of xn yn, instead it has this expression. So what we do is we add and subtract things that are not present in the original update, and towards that we first introduce this epsilon n, where what we do is we first look at the set of non adversaries, and wherever your expected value of y is there, we try to replace it yn and sort of subtract it. So I think there is a sign issue here. When I add epsilon n to this term and this term should cancel off, and to enable this I think I should have a minus here and a plus here, sorry about that, okay. And so we have some expression like this, and if you plug in h of xn and yn, you can see that this term and this term, right, will in some sense represent h of xn yn plus epsilon n, right, and if you take the conditional expectation of this expression, then one can see that you would end up with this term plus this term over here, making this mn plus 1 1 as a martingale difference term, right. So we want to analyze its convergence, and towards that we will make use of this Robbins Siegmund theorem, right. So I had told you that one can actually make use of the generalization of the ODE method in the context of differential inclusions, and somehow repeat the arguments that we had discussed in the context of the ODE method in the convergence analysis of stochastic approximation algorithms. However, my TA for this course and who is also doing a postdoc with me, Dr. Anik Kumar, okay, pointed out that maybe we can come up with a simpler argument for showing this result, and I agree with him. So the simpler argument is by invoking this Robbins Siegmund theorem. So what does the Robbins Siegmund theorem say? Suppose you have sequence of random variables on a common probability space. If I am not wrong, I think your Siegmund theorem also requires that all these random variables be non-negative random variables, and let us say they are all defined on the common probability space, and let us say these random variables are adapted to a filtration Fn, and further suppose that if you add these ANs they are less than infinity, and similarly if you add the Cn's up they are less than infinity almost surely. Furthermore, if you take the conditional expectation of xn plus 1 given Fn, then this is upper bounded by terms of this form, that is 1 plus An times xn minus Bn plus Cn for all n greater than 0. Then what this Robbins Siegmund theorem says is that almost surely your xn's will converge, okay. Furthermore, your Bn's will also be additive. Is this okay? So the Robbins Siegmund theorem says that if you have a sequence of random variables, non-negative random variables which satisfy these inequalities, right, then and furthermore these conditions are satisfied, then almost surely your xn converges and your summation Bn is finite, right. So now with this result in mind, right, we are going to derive a bound on this norm of little xn plus 1 minus expected value of x square, right. So whatever your capital Xn plus 1 was over here will now be played by this expression over here. So we want to obtain a bound on this expression which mirrors this form, and whatever An and Cn we construct indeed have these properties, so that we would be able to conclude these two things over here, right. So we will worry about what is the conclusion and so on and so forth. At this point we will try to derive a bound on this expression, right. Now recall that xn plus 1 has an update rule like this, so I can subtract expected value of x from both sides and then square it. So if I square it, the left hand side will be xn plus 1 minus expected value of x the whole square, and on the right hand side notice that I have like a plus b plus c plus d type expression, and I am taking the square of it. So first I will have some square here plus 2 times the cross terms. So the first cross term will be xn minus expected value of x transpose h of xn yn. The next cross term will be something like this, and the third cross term will be something like this, right. And finally I would need to take all these terms over here and square them up. I realize there is a typo here, so this should be alpha n square. Is this okay? So our goal would be to take the conditional expectation of the right hand side and come up with an expression that mirrors this structure over here, right. So towards this what we will do is we will define a sigma field which is basically made up of your initial estimates for x0 and y0, and furthermore we will include in it I1, y1 all the way up till in yn. In some sense this filtration or this sigma field, right, captures the information that we have until time n. So if you take the conditional expectation of this expression with respect to such an Fn, one can see that this expression is measurable with respect to this filtration, or this if you okay, I should not repeat it, this is measurable with respect to this Fn, and hence I can pull out all these terms from this conditional expectation and we will be left with this. And if you recall the description of Mn plus 1, right, in this expression and this expression, the difference is that you have your in plus 1 and you treat it as a random variable, imagine everything else to be a constant and only in plus 1 as a random variable, and if you take the conditional expectation you will get an expression like this. So because of this reason, if you take the conditional expectation of this will be 0, right. So let us go back. Our goal was to take the conditional expectation of this expression, and on the right hand side we had 1, 2, 3, 4, 5 terms, right. Now this term over here, right, is nice for our analysis, because if you take the conditional expectation of this term we end up with 0. Okay, so this leaves us with 1, 2, 3 and 4, and we will see how to deal with these 4 terms, right. So now what we will do is we will focus on this term, right. So if you remember, if I add these 3 terms I should get up an expression like this, because this is what our original update rule was, right. Now this sign expression, right, is upper bounded by, the absolute value of this expression is upper bounded by plus 1, right. So hence we will be left with norm of just this vector, and recall that AI transpose is the ith row of your matrix A, right, and this is the column representation of that row vector. So if you take the norm of this in plus 1, at most it can be A star, where recall we had defined A star to be the max of norm AI, right. So we had done something like this. So from this perspective I should maybe put a square here, sorry about that. Okay, so this square is actually A star square, okay, and I should have a square here as well. Okay, so from this what one can see is that forget about this. Okay, what one can see is that the left hand side whose upper bound we want to find is upper bounded by this term, we have not touched this term also we have not touched, right, and this term also we do not touch, but there were 2 other terms. So one of the terms conditional expectation was 0, so that vanished, and then there was this last term where we showed that it is now upper bounded by alpha n square times A star square, right. So let us look at this expression for the time being, right, and I hope you agree that if I sum it up, that is from n equals 0 to infinity, alpha n square times A star square, and because A star does not depend on n I can pull this off, right, and I would end up with something like this. So if I presume my step sizes are square summable, then indeed this expression that I have here will be less than infinity, right. So if you go back to that Robbins Siegmund theorem, right, whatever is the last term, I hope you agree that I can subsume it within Cn, because in Cn we require that this summation Cn should be less than infinity, right. So at least for one of those terms we can see that such a condition indeed holds. Okay, alright. So now in the today's class and the next class that follows, we will try to bound these expressions, that is the expressions that we have over here, right. So again we want to write it in a form so that we end up with some minus bn type cn type expression, so that this whatever is there within Cn, if you add it up, that will be less than infinity, right. So whatever we end up doing should enable us to apply this Robbins Siegmund theorem, right. So to derive bounds, especially on this expression, we need a technical result, and in today's class we will majorly focus on this technical result, and in the class that follows we will make use of this technical result and try to derive a bound on this expression over here. Is this okay? So what is the technical result? It says that suppose eta is defined in the following way, right. I will go over the details. So eta is some number, then the result says that whatever is this eta, this is strictly bigger than 0. Furthermore, if you define the constant k, right, in this fashion, so let us go over the terms here. There is 2 here, which is the number 2, there is q here, q recall is an upper bound on the number of adversaries, then you have and we presume that q is known, and A star is again an upper bound on the norm of your AJs, right, and divided by n times eta. So n is the number of rows in your matrix A. In other words, this is the number of coordinates of your vector y, and you can think of this as the total number of measurements that we have, right, or measurement sensors that we have, and this eta is what you have over here. And since eta is greater than 0, this quantity over here is finite, and what we do is we take this quantity and to it add +1. So this is your k, and the claim is that you give me any s, okay, which is a subset of 1 to n, right. You gave me any set S which is a subset of this and its cardinality S, okay. So at this point I want to keep it equal, and you give me any S such that its cardinality is equal to Q, then the claim is that such inequality holds, that is k minus 1. Notice that k is something plus 1, so k minus 1 will be strictly positive, so this quantity is strictly positive, right, times this expression, okay, and we are claiming that this should be greater than k plus 1 times this, right. And recall that S over here, right, is of cardinality Q, right. So presuming this Q is less than n over 2, right, one can see that we are looking at the sum of AJ transpose X on a small set of coordinates, and we are looking at the sum of AJ transpose X over the remaining coordinates, okay. So this expression, okay, is over a larger set of indices, and this expression is over a smaller set of indices. In particular, I can take S to be A, right, we will actually do that, but here I am insisting that this inequality should hold for every S. The reason being that I do not know which set of like S is which set of adversaries, that is something I do not know. So hence I am at this point trying to ensure that this inequality holds for every S, right. And I mean, if you think about it, right, what this inequality is trying to say is the following. So remember, we had some assumption on the A matrix, okay. So the assumption on the A matrix was that for any such subset S, if I take AJ transpose X, right, and take this sum over S complement, this should be strictly be bigger than summation J in S AJ transpose X, okay. This was the assumption that we had about A. In particular, we said that for all X not equal to 0 and any S such that cardinality of S is less than Q, right, I require that some inequality like this hold. Is this okay? So I require that some inequality like this hold, and here if you notice we have similar expressions to what I have here, okay. So whatever is this expression I have here and whatever is this expression I have over here, but I am not just saying that this is strictly bigger than this, I am instead saying that this expression by this expression is greater than k plus 1 over k minus 1. So this inequality over here is basically saying that if I take this left hand side and divide it by the right hand side, this ratio will be strictly be bigger than 1. Here on the other hand, I am sort of quantifying how big is this ratio guaranteed to be, that is, if I take this expression divided by this expression, then it is at least bigger than k plus 1 over k minus 1, right, and since the numerator is bigger than the denominator, that is k plus 1 is bigger than k minus 1, one can see that this ratio, that is k plus 1 over k minus 1, is going to be strictly bigger than 1. So in other words, whatever is the given assumption, right, we are sort of expanding on that assumption and trying to quantify, okay, is there some lower bound on this ratio that I can get. And the nice thing is this lower bound that we have over here, right, universally applies. That means for any x and s for which such a condition holds, right, indeed this relationship holds, right. So this k does not depend on the choice of x, right. So this, you will see how this helps. In particular, an inequality like this only says that this is bigger than this, but it is possible that maybe if I take a very crazy x, right, maybe this this ratio, that is left hand side by right hand side, is very very close to 1, right, and maybe I can get a number which is as close to 1 as desired, right. So what this result of ours tries to tell us is that won't happen. This ratio, irrespective of the choice of x, will be lower bounded by k plus 1 over k minus 1. Okay, so that is the conclusion that we are trying to derive over and above what is the assumption that was given to us, right. So now we are going to prove this inequality, and you will see in our subsequent class how does this inequality enable us to derive bounds on such an expression over here, right, and separately we will see how we can derive bounds on this expression as well. Okay, so let us try to prove this. I want to prove this, whatever be the value of q. So to begin with, let us presume q is 0, right. So if q is 0, which means there are no adversaries, then in that case one can see that k is equal to 1, like only in the case where q is 0 is k equal to 1, and for any positive number of integers k will be strictly be bigger than 1. So when q is 0, this left hand side is 0 because k is 1. Now let us see what happens on the right hand side. Because q is 0, right, whatever s you pick, this will be an empty set, and because this is an empty set, the right hand side will also be 0, and hence one can conclude that this inequality holds for the case where q is 0, right. So hence it only remains to see what happens when q is bigger than equal to 1. Now when q is bigger than equal to 1, from the definition of k one can see that k will be strictly be bigger than 1, that is what I have written over here. So now we want to prove this inequality, right. So towards that what we will presume is that this left hand side to begin with is, sorry, the right hand side, this expression is 0. Okay, so let us presume that this expression is 0. So if this expression is 0, well the right hand side will be 0. So since the right hand side is 0, whatever be the left hand side, since I have already shown k is bigger than 1, right, whatever be the left hand side, this inequality will trivially hold. Okay, so that is what I have mentioned here. If the summation on the right hand side of the inequality that we wish to prove is 0, then the result trivially holds. Okay, hence it only remains to consider the case where this summation is actually not 0. So I should say summation j in S, absolute value of aj transpose x is not equal to 0. Okay. So now if you look at eta's definition, okay, so let us recall eta's definition. So eta was min over S such that cardinality of S equals q, min over x not equal to 0, 1 over n times norm x, right, norm x times summation j in S complement aj transpose x minus sum j in S aj transpose x. Okay, so this is the definition of eta. So since eta is the min of all those things, so if you pick an arbitrary S, right, then whatever is this expression that you have, right. So since eta is the min of all these quantities, so if you pick an arbitrary S, right, this expression that you have over here will be bigger than eta, right. So if I just rearrange the terms now, and keeping in mind that your x is presumed to have non-zero norm, one can see that because eta is the min of this, eta will be less than this quantity for any arbitrary choice of x and s, and hence whatever is your s and x, this expression will be greater than n times eta norm of x, right. So now if I take this quantity that I have and divide on both sides, I hope you agree that I will end up with summation j in S complement absolute value of aj transpose x divided by summation j in S absolute value of aj transpose x is greater than 1 plus whatever n eta norm x is divided by the sum of j in S absolute value of aj transpose x, which is exactly this expression over here, right. Now and also I would like to highlight that I can actually divide by this quantity, because in this sub case that I am considering, I have presumed that this expression over here is not 0 and hence is strictly positive, right. Now from the Cauchy-Schwarz inequality we know that this expression that we have over here, right, and if I divide it by norm x from the Cauchy-Schwarz inequality, I know that this expression is upper bounded, right, by norm of aj by norm of x. So this x and this x will cancel off, and hence I will be left with sum of norm aj, and since we have presumed that A star is the largest norm, and since cardinality of S is q, one can see that this sum is upper bounded by q times A star, right. So this expression is upper bounded by q times A star irrespective of the value of x, right, and in particular we have presumed that x is having does not have norm 0, right. So from this calculation, that is this is less than this, one can show that this whole expression is greater than 1 plus n eta, which comes from here, and we have shown that this expression is less than q A star, and hence one can conclude that this expression over here is greater than this, which is greater than 1 plus n eta by q A star, right. And from the definition of k, one can immediately see that this expression equals k plus 1 over k minus 1, right, and since this expression is greater than k plus 1 over k minus 1, one can see that the desired result holds. Okay, so let me take you back. Okay, the desired result was basically something like this. Okay, so this is what we have indeed managed to show for k which is defined in this fashion, right. Now there is one part that is remaining to be shown, that is to show that this eta is actually strictly positive. I mean, I proved this result presuming eta is strictly positive. In the next class I will first begin by showing that indeed this eta which is defined over here is strictly positive, and then I will use this result to obtain a bound on this expression. Okay, so let me conclude today's talk, right. In today's talk we looked at this notion of this Robbins Siegmund theorem, which somehow said that if you had these random variables xn, an, bn and cn, and if it satisfied some inequality, then one can use certain conditions to talk about the convergence of xn, right. And we sort of said, okay, let us see if we can use this result to discuss the convergence of the stochastic recursive inclusions iterates, that is your little xn's, and that is what we started doing, and towards that we wanted to obtain a upper bound on the conditional expectation of xn plus the square of the norm of xn plus 1 minus expected value of x, and we did some preliminary calculations and we were able to see that at least 2 of the terms on the right hand side of this bound can be easily dealt with, right, and towards deriving bounds on the remaining one we discussed an intermediate result which somehow tried to quantify the mass that is there on the q many coordinates to the mass that is present in the remaining set of coordinates related to aj transpose x for any x, right. So we will be using these results to derive bounds on the remaining terms in the next class. Until then, goodbye and namaste.